Our speaker today is Ekaterina Glinyanaya with the talk Arratia flow is a Markov process with respect to spatial variable. Please.
Okay, thank you for introduction. And in this talk, I will discuss some properties of Arratia flows with respect to a spatial variable, and we will see what kind of questions and problems arise here. So I would like to start with the definition of the Arratia flow, just to recall what we are considering now. So we consider the family of continuous martingales that starts from each point of the real line, and with time the trajectories of these martingales do not change their order, and the joint behavior describes by the following equation for their joint quadratic variation. So from this, we can see that any martingale is a Brownian motion itself, and we can understand their behavior as following. So they any two trajectories or particles move independently up to their meeting, and after that they coalesce and became like one particle. So here is a simulation of such flow. So one can imagine how it looks like. And today we will consider the property of such system with respect to a spatial variable. So we will consider whole trajectories of the Arratia flow on some interval. For today, we fix it for 0, 1. So we fix time interval, and we consider the process that consists of trajectories. So x from u, this is a trajectory of Brownian motion in the Arratia flow that starts from the point u here. And today we will consider this process with respect to this variable u. Okay, so let's and as was mentioned in the title of the talk, we will consider this process as a Markov process. So this was proved by Darhovsov Andrei Anatolievich, and he shows that the process of trajectories in the space of continuous functions on the interval 0, 1 is a homogeneous Markov process. And transitional probabilities can be written using the following transformation of a standard Brownian motion. So if we consider the transitional probability from function u, so function y, this is the function, and maybe I will draw a picture for better understanding. So we have at point 0, we assume that our trajectory is equal to y. So this is y on the interval 0, 1, and we want to know.
But as I understand, y0 is not necessarily equal to 0.
It should be 0 here. Yes, right. So here it should be 0.
Here, but later on you wrote y0.
Yes, it's we do not need this to write because actually we can consider the transitional probability like from any point u from u0 to u0 plus h, but since the Markov process is a homogeneous Markov process, so we can consider the transitional probability from the function that starts from 0, and at point u it will belongs to some subset delta, like this one.
Maybe not this one delta, because if we glue up Wiener process with this function, it can happen that they merge before 1. Yes.
Yes, of course.
Such delta is not appropriate. Yeah.
But it can happen that it's not coalesce, so it.
Yes, yeah, but it can happen too. So it's better not to draw such picture. Yeah.
Okay, let me draw more appropriate picture. So if
maybe it's better to draw a function which occurs to be a random function which is
which
like,
can arise
which
here.
distribution is this probability.
Yes. So and the random function we have the this one, this function. So it starts from u, point u, and moves like a Wiener process before time of meeting the function y, and after that it becomes function y itself. So this is how we can describe the transitional probability for Arratia flow, or for trajectories of the Arratia flow on the interval 0, 1. So we just need to know the probability that this transformed Wiener process, so just glue up to the function y will belongs to some set delta. So now when we know this transitional probability, and it was put it, this is all. So the next question that arises here is about, I'm sorry, the transitional the transitions in the group of the of this Markov process. So as usual, we now can consider the space of trajectories I denoted by x, and we can define for bounded function f the following transitional probabilities, transitional sin group, as conditional expectation of the following form. So we take the function of the trajectory that starts from point U, and we consider the conditional probability when x from 0 is equal to y. So the question that arises here is about the properties of this transitional
Excuse me. Do we know that it is a strongly continuous semigroup as usual for good processes? So if we fix such f, do we have continuity with respect to u?
It is listed as the first question.
Yes. So this is the first question, and
no. This is actually. I think that maybe if we have the positive answer for any f, which is bounded and continuous on C01, then it was much easier to handle this semigroup, yeah? Because we can apply general theorems about strongly continuous semigroups.
Yes, I see what I'm talking about, but for now, to answer for this question, let me consider first example here. So the first example, how the semigroup acts. So I consider for fixed measure, I consider the integral with respect to this measure of a function y. And it's easy to understand how the semigroup T acts on this function. So we just consider the integral of the trajectory of the Arratia flow with respect to some measure with conditions that from 0 we have the trajectory y. So we split this integral into two parts, and here tau is the moment of the meeting of trajectory that starts from u and from I'm sorry, I should write here not x but y from. And so we have this one, and when I consider the difference t of u f minus f, what do we have? We have the first part remains unchanged, and for the second integral, if I write minus the integral from 0 to 1, I will have the integral from 0 to stopping time here, t u w t u y. So we have such expectation for the difference. So on the picture, what do we have? The picture. So we have that this action. This is t u f minus f. This is y at function y. So here we want to expect that this, so this is an area between these functions. So as we see, the answer is this area will tends to 0 when u tends to 0 depends on the point y that we consider. So because it can, if my y is decrease to like this too fast, then it can happen that of course for small u it can happen such picture. So this is about the continuity of the
but this function is not bounded. You consider linear functional. Yeah.
Why? It is bounded on 0, 1.
F itself now is linear function on C01, so it is not bounded at all.
Yes, but for yes, I understand it. But for F not bounded.
Maybe you can modify this idea, but now it is not related to the semi-group in the space of bounded continuous functions.
Yes, yeah, yes, I see what you're talking about. Yes, so maybe yes, I did not get the answer for this question or just fully. So. Okay, so this is the first example that we can see how the semi-group acts and what we can expect.
What problems we can get there?
Yes, yes, and what kind of problems we can get. And here the main problem that arises here in future, that the action of the semi-group is depends on the distribution of the first moment of time of the Wiener process to some function f. So this is quite difficult question about what we can say about the distribution of the first moment time of the for the arbitrary function here. So that's why we have quite difficult problems that arise here, but we can see something. So this is the second example that I want to consider, and for this one we consider for a fixed deterministic function the functional that that gives the integral with respect to a trajectory. Of course, this integral cannot be defined for any a, but let us just next we will we choose a such as that we want to take.
Katya, but what is the integral with respect to y if y is a continuous path?
Okay, on the next, what I want to consider, since we do not know much about the distribution of the moment of the first hit in time with arbitrary function UF, I want to consider the action of the semigroup not at the fixed continuous function, but at the trajectory of Arratia flow itself, so x0. So this is our next idea. So since we do not know for arbitrary y here the distribution of the first moment, but we know the distribution of the meeting of two independent Brownian.
So probably this function a of s, the integrand is a nice smooth function, and we can define the integral by parts, integration by parts. So in the first formula, yeah.
Or
Yes.
right, like Young's integral, right? If we know the path is almost 1/2, so therefore we need the regularity of A larger than 1/2.
Yes.
Yeah.
But
still, if it works for all continuous functions, I'm not that sure.
No. Yes, of course.
Yes, we can then choose A, whatever you want. But now I want to consider the action of the semigroup at not at the fixed deterministic function, but at the trajectory x0 itself. So this will be a random value now. So I consider this a conditional expectation, and again, it can be this integral I split to two parts, before the moment of heating and after. Before moment of the heating, I know that we know that since trajectories has covariance 0, for s less than tau, and the trajectory are equal for s bigger than tau, then I have that the first expectation is just 0, and for the second expectation, I can write the following. So I just write the integral with respect to dx0 here. So here, if we want to understand the behavior of the semigroup, we need to understand the behavior of this conditional expectation of the first moment of the meeting of two trajectories in the Arratia flow. So to do this, now, if I want to consider how fast the action of semigroup will converge, if it will converge to the function f, I consider the following difference. So now I get that the difference is equal to minus integral of a, and here conditional expectation of tau u greater than s dx from 0. So since we have here random value, we will investigate the speed of convergence when u tends to 0 of such value in L2. So and to do this, I will at first write down this conditional expectation of the indicator that first moment of the meeting greater than s, with condition on the trajectory x0, I will write this conditional expectation as with series expansion with respect to multiple integrals with respect to Brownian motions. So this is a statement that allows us to represent the conditional expectation in such form. So here, let us denote by x w1 is the trajectory that starts at 0, and x2 the w2 the trajectory that starts at point u, and tau will be the first meeting of time of two of these Wiener processes. And then the conditional expectation can be presented in such series of multiple integrals with respect to w1. Here, capital G is the function of the following form. So this is the density of Brownian motion that starts from x and goes to y without hitting 0. So how we can get this series expansion? So we can use, so here I use two steps for this proof. And the first, for one Wiener process, I will write the eta Wiener expansion for the indicator for the moment of the time tau, where this, so I consider the first moment when u plus wt hits 0. This one. And this series expansion is of the following form. So we have the sum with respect to sum of multiple integrals with respect to this Wiener process. And it can be done using the application of stochastic exponent. And if we know the solution of such a function when we multiply our random variable by stochastic exponent, then we will have the series expansion for random variable itself.
Only you have to write not h but phi or vice versa instead phi or something.
Here I
maybe because of fuzzy you use. Okay.
Thank you. Yes. With such notation, yes, sure. With such notation, we have that the function will satisfy the following boundary problem, and here, and we have solved this boundary problem in terms of the series that appears in on the previous slide. So this is the idea how we can, I'm sorry, how we can get this series expansion of multiple for the random variable in form of multiple integrals with respect to w. Okay, and the second step, if we have two independent Brownian motions, and we want to write down the conditional expectation for such indicator, I'm sorry, of the first meeting of the time, then we will have just such series, and here we can see that appears -1 to the power k, and this function ak, they are from the previous expansion. I didn't write down them. So we know this, the expansion of this conditional probability. So let us come back to our problem. So what we will expect in the limit for the action of the semigroup and minus f divided by u. I recall how function f looks like, and we have in the difference here we have the following series. So here we integrate with respect to s such terms. Here ak us is the following integrals with respect to trajectory x0. So we can denote it by Wiener process. And if we want to get some limit when u tends to 0, we will expect that each term that divided by 0 by u will tends to some limit. So let's consider what we will have, and if we will have the limit of the following form. So I divided by u and consider this integral of the each summand in the house expansion, and I put this limit under the integral. Of course, we do not know if it's okay to do this, so I put it here because I just want to understand what we can expect here. And the terms that depends on u is just the first multiplier in this integral, and I just want to take the limit of g of u divided by u. And it can be seen not that the limit of g of u divided by u is equal to such value. Now let us substitute this value into the integral with respect to w. And the first question, if we have the good integral. So consider the first term when we have just such integral. So here I take the I just want to mention that here I take the limit when u is tends to 0 of the integral of this integrals u. Yes. So I put this when u tends to 0. And to understand that the limiting integral is well defined, we need to check that this function that we have here under the integral is square integrable with respect to t. So we need to check that such integral convergent, and unfortunately this is not true. And to see this, actually we can calculate this integral with respect to a spatial variable. And this integral is equal to such expression. And if we substitute it to the integral...
There is a in this expression.
I'm sorry?
There is a of s. It is somehow eaten.
Oh, a
yes, it was some unknown function, a of s.
Yes. Since here the integral with respect to y.
Okay.
Yes, I just will not write here. It appears here. But nevertheless, when I consider such an integral, it will divergent for any function a. So it just divergent when we consider this first integrals with dt2, dt1, and the function a does not help us. So we saw that the behavior of the function a at 0 will help us, but not so. The conclusion of this example is the following. So for
I'm sorry, I have one question.
Okay.
I did with Professor Drogovtsy, we did a very similar calculation in our last paper, and if it were not for the square, it would be convergent without stochastic part, right? And there is a way to define a stochastic integral if it's not in L2 still.
So what is your question? That you can define the stochastic integral without...
Probably in the same sense that Lipser and Shiryaev did in their monograph on statistics of random processes.
Okay, so...
That's all.
I mentioned to Katerina our calculations. Yes, it is very closely related, but I did not understand your statement that stochastic integral can be defined because you see, we can try to define at least Ito integral for a locally square integrable function such
yes,
that...
Yes, exactly.
Yes. But in this case, we have to study this very carefully because we are checking the deterministic kernels, and we need integrability with respect
to many.
Yes, multiple which respect not one Wiener process but two rather. So we have to formulate some statement more precisely, and even if we do this, you see, we considered the term of Ito Wiener expansion. if we have the limit, for sure it must be in L2. For sure it must have the kind like integral, multiple integral from something.
I see.
If we have convergence, we have to have limit. So here we have negative answer, at least with respect to L2 convergence.
I see. Thank you. I mentioned our work because this is why I think it's finite.
Exactly, and I also mentioned it to Katerina, and maybe Katerina already have it.
Yes, I look at it, but since
No, I just mentioned it because I remember these calculations and I know that it's finite, at least in some sense. That's all I'm telling. You may not need it here because it's actually the idea from a paper of Izumtsev, Drogovtsev, and Salhi. You just modify it to calculate. Thank you.
Okay. So for this case, when we have the function, when we have the function of the following form f, and when we consider that the value of semigroup at trajectory of the Arratia flow that starts at 0, we do not have the limit for such case. So this means that.
Sorry, but do you know anything about this probability of tau u bigger than t? Probably it compensates the divergence of all other summands.
Yes, of course, we know this.
So it doesn't compensate.
It does not.
It cannot compensate because here we have e-to-winner expansion. By the way, it is written here shortly. AK are orthogonal, so it cannot compensate.
Okay. So this is the zero term to this extent.
Yeah, this is just zero term.
So we have such a negative example for the function for which we do not have the convergence for the, and we do not know the action of the generator of the semigroup. And the next part that I wanted to talk about, this is about the application of the general theory of the semigroups, but unfortunately I did not manage to prove that our semigroup is indeed strongly continuous semigroup. Here so for now I can say that we can apply this theory that tells us the form of dense subset of the domain of generator for strongly continuous semigroups, and so I don't know if I need to continue. I considered some examples of such form. So what does this theory say? That if we have a strongly continuous group, then we can write the dense subset of the domain. So the set of function for which we have the convergence of such form. And these functions are given in the form of the integral with respect to, in our case, u. And we know the action of the generator on the function of such form. So I considered some example just for how does such functions looks like, just to understand what we can expect if we have the property of strongly continuity of the semigroup of the Arratia flow. So if we consider again the function that defined as integral of some deterministic function a, and then how does the function of the following form looks like? So if we have the integral with space variable, we just consider the conditional expectation, and we can write it in such form. And as I say, for now, I don't know this because I do not know the property of strongly continuity of the semigroup T. But nevertheless, we can see how does this function U looks like. So I just draw the picture of. So we have the integral. If for simplicity, I take the constant function a, just one, then we have just the difference at the point moment time 1 and 0, and the function u is just the integral with respect to spatial variable of the function x u at point 1. So how does it look like? So if I have the Arratia flow of the following kind, and I assume that we have at 0 some function f, then this function u from f will be the integral. So we just write this, draw this integral of the step function with steps of the size this one. So this is values are here. So this is the moments of discontinuity of the Arratia flow at point 1, and the height of the steps is the values of the Arratia flow at point 1, at time point 1. So if we will know the strongly continuity for the semigroup, we will know that this kind of functions are in domain of the generator of the Arratia flow. So we can write this function, how it looks like. So we can write this function as an expectation of, I just write down here the integral where theta are points of discontinuity of the step function x, and psi are the values of the function x. So here we can see that we have quite difficult dependence on a function f here. We have such a function that just build the mean of such integral of that step function. And of course, here again, the main difficulty that we have is first moment of the meeting to the point, the function f here. But unfortunately, for now, I don't know if the generator is well defined even on these functions. So this is what I will work on in in the future. So I think that's all what I wanted to say for today. And thank you for your attention.
Okay, thank you very much. I have some questions. Maybe it will be good from general point of view to consider this process from the point of view Dirichlet form. Do you suppose to do this, or you did already?
Yeah, I suppose to do this, and for this we need to understand the what is the form of invariant distribution of the transitional probabilities, right? So for now, I just I started to consider this, but again, I did not finish that part of the work, of my work.
Okay, and the next one is maybe you can present us motivation of this consideration. Why we went to consideration of this spatial dependence of Arratia flow in Arratia flow.
Okay, so the motivation was the following, that we wanted to investigate the point process that arise at some fixed point, let's at point 1. We have the values of the Arratia flow, and we have this point process itself. And the question that I considered previous time was about the integrals with respect to this point process. So let eta be a point process of the Arratia flow at point at time t is equal to 1, and we can define the multiple integrals with respect to ek of x. Usually for point processes, we write here factorial powers of the point process. So I write like this. And we wanted to find the orthogonal decomposition for the space of the m factorial integrals. So this was the first question, how we can find the orthogonal complement for space of two-dimensional integrals and so on. And it turns out that it quite we had a problem with finding the orthogonal complement of the space of all two-dimensional integrals to the space one-dimensional integrals. So this is orthogonal decomposition we wanted to write. So, and in order to understand how we can investigate this multiple integrals to the points at the moment time 1, we started to to investigate the covariances between the random variables of the form that we want to find the number of points on the integral of the interval on the form, like and k minus 1, and let it be random variable c.
Maybe k plus 1. Yeah. Mm-hmm.
And even in order to find the covariances between these random variables k plus 1, and so we wanted to find the orthogonal decomposition of the integrals if we know the covariances for number of points in small intervals, small but close together. And when we consider such covariances, it turns out that it's not enough to know just the distribution of just we need to know the trajectory of all Arratia flow itself, and we need to understand if we start from close paths, close points, the probability is that the trajectories will coalesce or not coalesce. So
you now are speaking about dual process.
Yeah. Maybe yes. So
yes.
Here,
so,
if we consider this,
so you have to start from the right line. Yeah.
Yes, from this one. And we need to know if for 2 points that are close enough to 1, we need to know if they meet or not. And in this case, we started to, so with this motivation, we started to consider the
maybe
of the Arratia flow.
Maybe it's better to note that to calculate the covariance, we need to control together 4 trajectories, which start from ends of these 2 intervals at least. Yes, in the dual flow. So this was the reason why we are not simply considering usual picture with 2 trajectories which coalesce or not.
Yeah? Yes, we should know much more trajectory.
Okay, this was the motivation. Thank you, and maybe somebody have comments or questions, please.
May I ask to show the slide with, there was a list of 3 questions somewhere in the very beginning.
Yes, sure.
So probably you can give a summary as what happens with these questions. A summary, because so, I don't. Yeah, so first,
Yes, for now, what do we have? So for now I did not check the strong continuity for the same group, and even what class of functions will have the limit here, and what is the speed of convergence, I still don't know. So it was our idea to understand the class of function on which we will have convergence and to find it convergence, and this now it's still the questions.
Okay.
Thank you. Some other questions, please?
I have a question. Could you please go a little forward? Yes. Oh, here. So you have this decomposition.
Mhm.
and you try to differentiate it with respect to u, and it fails to converge, right? Formally, term-wise.
Once more,
If we go a little further,
yes.
here you have this representation, you have this, and then you try to find the derivative of this expression with respect to u.
Right, yes. And when I write here so I divided by u,
yes,
and go and take the limit when u tends to 0. Yes.
It fails to converge term-wise, but if you return one slide back, or maybe 2 slides, or maybe 3, here, it's a solution of this one forward. Yeah, but it solves this PDE, right?
Right.
Yes, Nikolai, it is a very good question, and you can state that Fourier-Wiener transform has the derivative. In this case, I mentioned to Katerina that maybe it will be very good and to discuss the existence of the derivative and generator of our process, Arratia process with respect to spatial variable, in a sense of generalized Wiener functionals, because here we understand that in some sense, in some weak sense, derivative exists. Yes, you are right. Yeah.
Exactly. Thank you. This was my point, my question. Thank you.
Okay. Maybe some other questions, please. If there are no questions, thank you, Katerina, again, and we hope that next time we will see interesting results about this process and its generator. And who will be the next speaker? Maybe Georgi, do you know?
Yes, it will be me.
Oh, right. Okay, so we will see you next time as a speaker.
Yes.
Not only as organizer. Okay, thank you, and see you next week. Bye.
Thank you. Bye.